Welcome to the Crazy Hat Chemist. Here we go. Today is the 9th video in a series of 16 dealing with gases. Today we're going to be talking about Dalton's Law. So here we go. Dalton's Law of partial pressures. The total pressure of a mixture of gases is the sum of the partial pressures exerted by each gas in a mixture. When you see the words collected over water, you know that when a gas is collected over water, you're going to be using Dalton's Law. Okay? Each gas exerts its own partial pressure that is independent of all the other gases in the mixture. So that makes this a really cool law. So here we go. PT, that's pressure total, is equal to the sum of the pressure of gas 1 plus the pressure of gas 2 plus the pressure of gas 3. Typically, you'll see it in this type of equation. That is, the total pressure is equal to the partial pressure of the water, that's pH2O, plus the pressure of all the other gases, P2 plus P3, etc. All right, let's see how this is applied. So if you have 0.5 moles of hydrogen, 0.5 moles of nitrogen, and 1 mole of helium, they're all placed in the same container, giving an internal pressure of 860 millimeters of mercury. What is the partial pressure in millimeters due to the hydrogen gas alone? So the total pressure, that's PT, is equal to the sum of all the individual pressures. So PT is equal to pH2 plus PN2 plus PHE. Notice that the hydrogen and the nitrogen are both diatomic gases and the helium is a monatomic gas. So we're going to substitute in the total pressure for what the total pressure is. That's the 860 millimeters of mercury. Then we know the mole values, and that is a mole relationship between the hydrogen, the nitrogen, and the helium. So we're going to plug in those values, but in terms of x. We're going to sum these values of x together, so that's 0.5 plus 0.5 plus 1, that's 2x. And now we're going to solve for x. So 860 is equal to 2x. Divide by 2 on both sides, and then we're going to get x is equal to 430 millimeters of mercury. So now we have to ask ourselves, what does x equal to in this equation? And this is actually just the pressure of the helium gas. So we've solved for the pressure of the helium gas, but you should see that 0.5x, which is the partial pressure of the hydrogen gas, and that's what we're asked to solve for in this problem. So we need to find half of 430. So half of 430 is to 215. So that is the partial pressure of the hydrogen gas. It just so happens that the nitrogen gas has the same mole value, so the partial pressure of the nitrogen gas is that of the hydrogen gas. They're the same. Here's a good check. So we know the total pressure is 860. We know the pressure of the hydrogen gas is 215. We know the pressure of the nitrogen gas is 215. And we know the partial pressure of the helium gas is 430. So they should all sum up to 860, and that should make sense. Hopefully that check really works for you. All right, let's go on to the next problem. Here we go. So, what is the pressure if the gases in cylinders A, B, and C are all combined into one cylinder, that is cylinder X, assuming the same type of cylinder, i.e. the constant volume. So cylinder A, as you can see from that diagram, has 100 kilopascals of gas in it. Cylinder B has a pressure of 250 kilopascals, and cylinder C has a total pressure of 200 kilopascals. Cylinder X is empty, and we're going to combine all three gases from cylinders A, B, and C into cylinder X. So that is, the total pressure in cylinder X is going to equal to the sum of the pressures of cylinders A, B, and C. So we're going to sum up these values. That's the 100, the 250, the 200. We're going to sum those up, and we get 550 kilopascals of gas, and that would be the total pressure in cylinder X if you place the gases from cylinder A, B, and C all in cylinder X. All right, hopefully that works for you too. Let's move on. So this is an excellent problem, and it really works when you're doing a lab. So that's really typically the name of the lab is the molar volume of a gas lab. So let's read the question. It's 15.4 milliliters of hydrogen gas is collected in a gas measuring tube over water. The temperature at the time of the experiment is 26.0 degrees Celsius. The vapor pressure of water at 26 degrees Celsius is 25.2 millimeters of mercury. That's actually a tabled value. You would have to look that up in a table or given to you like it is in this problem. The pressure of the room at the time of the experiment was 779.5 torr. That's actually a measured value from a barometer in the room at the time of the experiment. And then it says, what is the volume of the dry gas at STP conditions? So an experiment here is like you see in that diagram. You have a beaker filled with water. You have a gas measuring tube. At the very bottom of it is filled up with typically hydrochloric acid hydrochloric acid, a liquid at 6 molar, and then you layer it with water. Inside that, you place magnesium ribbon wrapped with copper wire, and then you invert the tube so that the hydrochloric acid falls down and then reacts with the magnesium ribbon and produces hydrogen gas. It's a single displacement reaction, so the magnesium and the hydrochloric acid are producing hydrogen gas and magnesium chloride in solution. And so you end up displacing the water inside the gas measuring tube, and you fill up part of the tube with hydrogen gas. So that gas is collected over water. So that over water is letting us know that we're going to be using Dalton's Law. So make sure that you review what you have as far as the numbers on this slide, and let's do the math associated with this problem. There's 2 steps to this problem. The first one is to find out what the partial pressure of the hydrogen gas is, and then after you figure out the partial pressure of the hydrogen gas, that gas is over water, it's collected over water. Then we're going to put it into the combined gas law and solve for the partial pressure of the hydrogen gas and that's dry under STP conditions. So here we go. So the total pressure is equal to the partial pressure of of water plus the partial pressure of the hydrogen. And we know the total pressure, that was measured, and we know the partial pressure of the water, and that was a tabled value. Those 2 values are in the problem. We're going to solve for the partial pressure of hydrogen, so it's a simple subtraction problem. You notice that both of these numbers here have to 1 decimal place, so my subtraction will end up having 1 decimal place as well. So my partial pressure of hydrogen gas at 754.3 torr. This hydrogen gas is collected over water, so we call this wet gas. So now what we're going to do, this is the first step. Now we're going to plug this into the combined gas law. Here's the combined gas law. We have the pressure of the wet times the volume of the wet divided by the temperature of the wet is equal to the pressure of the dry gas times the volume of the dry gas divided by the temperature of the dry gas. I've highlighted what we're solving for, and that is the volume of the dry gas. On that right-hand side, we know that dry gas is at STP conditions. So that's standard temperature and pressure, and hopefully you remember that the standard pressure is 100 kilopascals, and the standard temperature is 273.15 Kelvin. So those numbers go on that right-hand side, replacing the pressure and temperature respectively. So now what we're going to do is we're going to convert that 754 torr into kilopascals. And here is that conversion. The 754.3 torr has 4 significant figures. I'm going to maintain 4 significant figures after I do this unit conversion. So there's my unit conversion with the 760 torr and the 101.325 kilopascals. Both the 760 torr and the 101.325 kilopascals have an infinite number of significant figures. Now I'm going to plug that kilopascal value in and convert my temperature and plug into the combined gas law. So I got the 100.6 kilopascals. The 299.2 was the temperature of the time the experiment was taken, converted into Kelvin with 1 decimal place. I had 15.4 milliliters of hydrogen gas that was collected over water. So that's why that whole left-hand side of that equation is wet conditions. You see the right-hand side of the equation is 100 kilopascals, the 273.15 Kelvin, and then we're solving for the dry hydrogen gas volume. So we're going to look at significant figures. We've got the least number of significant figures. That's 3. So my answer is going to have 3 significant figures. So here's my answer, and that is the volume of the hydrogen gas that is dry is 14.1 milliliters. It has 3 significant figures. I hope that problem worked out for you. Make sure that you check that temperature conversion there from the previous slide, and you can check that out. All right. So, I hope you enjoyed that video. That was Dalton's Law. Dalton's Law deals with partial pressures of gases. And that was the 9th video in a series. The next one you need to look for, and that is Avogadro's Law, and that is the 10th video in the series. How do you like this hat? I love it. You have a great day. See you next time. Bye now.